Let's talk about finding the zeros of a polynomial function using the Descartes rule of signs, the rational root theorem, and the remainder theorem. Here is our problem for today. Find the roots of p of x equals x to the fourth plus x cubed minus 19x squared plus 11x plus 30. We can employ some theorems that can narrow down our search for the roots. One of them is to use the Descartes rule of signs. If we let f of x be a polynomial function with real coefficients, meaning the coefficient a sub n is a real number, then the number of positive real zeros is either equal to the number of sign changes of f of x or is less than the number of sign changes by an even integer. And the number of negative real zeros is either equal to the number of sign changes of f of negative x or is less than the number of sign changes by an even integer. Let me demonstrate the meaning of Descartes' rule of sign using our problem. Let's count the number of sign changes in our given polynomial. So here you have positive x to the fourth going to positive x to the third. There is no sign change. So there is zero sign change here. From positive to negative, there is one sign change. From negative to positive, so we have a total of two sign changes. And according to Descartes' rule of sign, we can expect two positive roots or less than this number by an even integer. What are the even integers? That means if I subtract 2 by 2, I get 0. I can also have 0 positive real root. So we'll just ignore those negative numbers. We expect to get either 2 positive real roots or 0 positive real root. Let us organize the number of positive, negative, and imaginary roots in this table. Since the degree of the given polynomial is 4th degree, using the corollary to the fundamental theorem of algebra, we expect to get a total of 4 roots. And these 4 roots could be a combination of positive real root, negative real root, and imaginary roots. And also take note that imaginary roots always come in pair. So we can have 2 imaginary roots, 4 imaginary roots, but you cannot get 1, 3, 5, 7, and so on imaginary roots. The number of imaginary roots must always be even, but the total is always 4. Now, for the negative real roots, we find p of negative x. That means replace the variable x with negative x and simplify. And so p of negative x is now equal to x to the fourth minus x cubed minus 19x squared minus 11x plus 30. A faster way of getting p of negative x is whenever you have even exponent, just copy that term, and when you have an odd exponent, change the sign of that term. So here the term preceding x cubed is positive, we make it negative. The term preceding 11x is positive, we make it negative. And all the rest, we just copy it. Then let's count the number of sign changes. From positive to negative, there is one sign change here. From negative to positive is one sign change. And so we have a total of 2 sign changes of f of negative x. That implies that we can either get 2 negative real roots or less than this number by an even integer. We can either get 2 or 0 negative real roots. This table now, the combination of positive, negative, and imaginary roots, based on the fact that we can have a maximum of 2 positive real roots and a maximum of 2 negative real roots. We come up with these 4 possible combinations. Either you have 2 positive, 2 negative, and 0 imaginary. The total is 4 roots. The positive roots could be 0. That means the rest are negative and imaginary. An imaginary root must always be even number. If there are 2 positive and 0 negative, there must be 2 imaginary roots. If there is no positive real root and no negative real root, then all the roots must be imaginary. So the Descartes rule of sign just tells us the nature of the sign of roots that we are expecting, but this does not tell us what are the roots. So we need to use the other theorems. The next theorem that we're going to use is the rational root theorem. It says that the possible rational roots of a polynomial function is a factor of the ratio of this constant and the coefficient of the leading term. So the ratio of 30 over 1. And what are the factors of 30 over 1? All the possible factors of 30 over 1 are listed here. A total of 16 possible rational roots. And take note that we are looking for 4 possible roots, either positive, real, negative real, or imaginary. But here, we have 16 possible candidates for the rational roots alone. So we need to narrow down the number of roots. If we're going to plot all those possible real roots on the number line, this is what we saw. Let's remove the label so we can make it more. Our function is an even function because the highest degree is x to the 4th. The graph of our function look like this. This graph will not cross the x-axis. We have imaginary roots. Graph will cross the x-axis. And the points of intersection represent the zeros or the roots of the polynomial function. From this point going here, the function just keeps going up. And at the left side, from this point going to the right, there are no longer roots. And at the left, from this point going to the left, there are no more roots. We can now say that there could be an upper bound here and a lower bound for the real roots of this polynomial at the left side. And if we can identify this lowest integral upper bound and this highest integral lower bound, we can narrow down our search for the roots in this part. That is what we are going to do next. Let's search now for the upper bound. Not good to test 30. If we found 30 to be an upper bound, 30 is really at the right side. But if we can find, let's say, positive 5, and if 5 is an upper bound, then we can eliminate 6, 10, 15, and 30 for the possible roots of the function. Also for the lower bound, if we can identify a lower bound, let's say negative 6 is indeed a lower bound, then we can eliminate negative 10, negative 15, and negative 30 for the possible candidates for the real roots. That's the function of identifying the upper bound. We want to narrow down our list of possible real roots. Let's test if 5 is an upper bound. In order to do that, we are going to perform synthetic division, and we are going to look at the signs of the terms in the last row. If all the signs in the last row are positive, then we will conclude that our divisor is an upper bound of the polynomial function. So let's perform our synthetic division. Let's bring down 1 multiplied by 5 to get 5, get the sum of 1 and 5 to get 6 multiplied by 5 to get 30, then add to get 11, multiply by 5 to get 55, get the sum to get 66, and multiply by 5 to get 330, and finally get the sum to get 390. Look at the signs of our numbers at the last row. You have positive 1, positive 6, positive 11, positive 66, and positive 390. All of them are positive numbers. Because these are all positive, our conclusion is 5 is an upper bound. And so, we can now eliminate all these possible rational roots, 5, 6, 10, 15, and 30, because we know that 5 is an upper bound. The function will just keep going higher and higher after x equals 5, and the graph will no longer turn down to intersect the x-axis. Just using this one test, we now narrow down the possible number of rational roots from 16 down to 11. If we try the next integer lesser than 5, that is 4, notice that if we perform the synthetic division, the last row also are all positive, which means that 4 is also an upper bound. Now let's try positive 3. Using synthetic division, notice that the last number here which is the remainder, is 0. So using now the remainder theorem, we now conclude that 3 is a rational root. 3 is not an upper bound, but 3 is the root that we are looking for. So we now found one solution, that is x equals 3. And by knowing that x equals 3 is a solution, then 4 must be the lowest integral upper bound. Any value of x greater than 4 is an upper bound, and 4 is the lowest integral upper bound. Now let's try for negative roots. Let's pick any possible roots here. Let's say negative 6. If we try negative 6, notice the signs in the last row. You have 1, negative 5, positive 11, negative 55, and positive 360. There is an alternating signs from positive to negative, back to positive. When the signs in the last row of the synthetic division is alternating, then this divisor, in this case negative 6, is now a lower bound. It could be negative, positive, as long as the signs are alternating. Then we say that whatever is the value of our r, that possible root is considered as a lower bound. And that eliminates negative 10, negative 20, negative 30, and negative 15 for all the possible negative roots. By just using these several tests, we now know that our focus for the search of the root should be on this middle part, because anything to the right of that is an upper bound, and anything to the left of this is a lower bound. We only have to choose among these possible roots that are encircled. And those numbers are 3, 2, 1, negative 1, negative 2, negative 3, and negative 5. And previously, we already identified positive 3 as one of the positive roots. And then let's try some of these remaining possible rational roots. Let's go back to the depressed polynomial when we found that 3 is a root. In the depressed polynomial, represented by this 1, 4, negative 7, and negative 10, this negative 10 is the constant, this is the linear term, the quadratic term, and this is the cubic term. So the highest exponent now here is 3. Using negative 5 in our synthetic division, the remainder is 0. Negative 5 is one of the roots that we are looking for. So negative 5 is a root. We need 2 more. In our Descartes rule of sign, we expect either to have 2 positive or 0 positive. And we also 2 negative real roots or 0 real root. We do not expect to get only 1 positive or 1 negative. We are looking for that other positive root. We are looking for that other negative root. If negative 5 is a root, and if negative 6 is a lower bound, then anything to the left of negative 6 cannot be the root. Negative 6 now must be the highest integral lower bound. There is no more number greater than negative 6 that can be a lower bound for the roots of this polynomial function. At the last row of our depressed polynomial, this negative 2 is the constant, this negative 1 is the coefficient of the linear term, and this positive 1 is the coefficient of the quadratic term. So what we have a quadratic depressed polynomial, which we can solve using factoring. This 1 is the coefficient of the x squared, this negative 1 is the coefficient of negative x, and this negative 2 is here. So finding now the series of this quadratic equation, we can factor the left side as x minus 2 and x plus 1, and solving for x equals positive 2, and x equals negative 1. Combining these results with the other 2 roots that we already found, we now have these 4 roots. 2 and 3 are both positive, negative 1 and negative 5 are the 2 negative real roots. All in all, we have a total of 4 roots, which is consistent with the highest degree of our given polynomial equation. And these 4 real roots are all contained in this circled interval, which we narrow down by applying the integral upper bound and the integral lower bound. The roots now of the equation x to the 4th plus x to the 3rd minus 19x squared plus 11x plus 30 equals 0, negative 5, negative 1, 2, and 3. The highest integral lower bound is negative 6, this part here. And the lowest integral upper bound is 4, this part here. And going back to the Descartes rule of sign that we used at the start, we have here two negative real roots, which is consistent with these two. We have two positive real roots, which is consistent with these two, a total of 4 roots and 0 imaginary root. And finally, if you are going to graph now the polynomial function, these 4 roots that we identified are the following: negative 5, negative 1, positive 2, positive 3. Geometrically, all these roots are the x-intercepts of the function. These are the points of intersections between the curve and the x-axis. And for the lower bound, negative 6, the graph just keeps going higher and higher. And for the right side, an upper bound of 4 here indicates that the graph will just keep going higher and higher without turning back anymore to intersect our x-axis. So that is the systematic way of finding the roots of polynomial function. You do not know among the possible rational roots are the real zeros. You have to narrow down all the possible roots whenever you identify the upper bound and the lower bound, and then you just keep performing synthetic division until you arrive at a zero remainder in order to apply the remainder theorem. And whenever you get a remainder of 0, use the depressed polynomial in order to continue finding all the other possible rational roots. And when you are down to a quadratic depressed polynomial, use quadratic formula, factoring, or any other method to solve quadratic equation in order to find the last 2 remaining roots. Thank you very much, and we hope to see you again in our next video.